So, Chapter 2 is trigonometry, and we're going to start off with the basics of trigonometry, which is basically angles in standard position. So, this section will go over something called a reference angle, okay, right here, reference angle, and we'll also go over where the quadrants are, where the different quadrants are, and the three trigonometric ratios: sine, cosine, and tangent. Okay, before we get going though, why study trig? Okay, why study it? Well, basically, okay, measurement problems is the big application of trigonometry. So you've done measurement problems before in building designs and so forth. In today's technology, it takes it a stage further, and we talk about something called Fourier analysis. Now, this is higher level mathematics, in university. But you can see I listed off some of the applications below, which all are very, very useful. In our own lives, imaging and signal processing are used all of the time. So, for instance, the JPEG image conversion is, JPEGs are used all the time to basically compress an image so that the quality is pretty good, but it's small enough that you can take a lot of photos. How this works is basically using something called a Fourier transformation. Okay, and you can read through this, and it gives you a very roundabout or qualitative understanding of how this works. But basically what a Fourier transformation is, it's a combination of sine and cosine functions. So here's a JPEG image. You can see the quality, and here's the raw image. The quality is much less than JPEG, okay, but also the size is much smaller than the raw image file, which would be what you would see. Okay, so this is just an application. JPEGs are not the best, right? Not the best, but maybe the best bang for the buck in terms of size. So let's get into it. The Cartesian plane. The Cartesian plane is basically this coordinate system right here. XY coordinate. This is quadrant 1, 2, and of course 3 and 4. Now, let's get my pen hooked up here. Basically, the initial arm, which is right here, and the terminal arm, that's all we really care about. I'm just going to draw terminal arms, and the angle made by that, we're going to represent it with the Greek letter theta. This is an angle in standard position. Okay. A reference angle is the angle closest to the x-axis. In quadrant 1 right here, that will be whatever the standard angle is. Okay. In quadrant 2, here's the standard angle. The reference angle is different, right? This is the closest angle to the x-axis. You got to understand this. We're going to use this all the time. Finding reference angles. In quadrant 3, it's right here. Okay, it's not the full angle. Quadrant 4, here's the reference angle. We denote it with theta, r. Okay, reference angle. So here's some pictures. All of the angles, okay, all of these angles have a reference angle of 20. You can see the difference. Here's the terminal arm, and the terminal arm is over here. Different positions, reference angles are, of course, the same. Right? Same reference angles for both of them. When you look at quadrant 3, quadrant 4, reference angles are the same. So, let's do some sketching. Okay, first of all, let's do some standard angles in standard position, which basically just means draw them: 36, 210, 315 degrees. You can look at the solutions, and the quadrants are pretty easy to tell. I'll do some practice problems here. So, question A, 150 degrees. Okay, well, let's draw 150 degrees. And this will be, as you probably could tell, in quadrant 2. I'll draw the Cartesian plane, switch colors, and 150 is right around there, right? And that is your angle theta. Not the greatest picture, but you get the idea. Okay, the next one's 60 degrees. This will be for B, 60 degrees. Again, you draw your little coordinate system. 60 degrees is going to be in quadrant 1. Right? Something like that. Above 45. And B is 240 degrees. Yeah, you're going to have to be familiar with this Y right here. That is 90 degrees. Then we have 180 degrees. Rotation here. 270 here. So 240 will be somewhere around here. Okay, and that's how you draw the full angle. Okay? And that's that. Moving on. Moving on to determining a reference angle. Well, angle closest to the x-axis. I can't drill that in you more. Closest to x-axis. Okay, that's what we're looking at. Closest to x-axis. So when you look at the practice problems and you look at 75 degrees, 75 degrees is, if we draw our coordinate system, 75 degrees is roughly here. Okay, now this is quadrant 1, right? This is quadrant 1. Theta in this case, 75 degrees, and theta r are going to equal the same. Theta is going to equal theta r. Okay, they're both going to be 75 because this is the closest you can get to the x-axis. In quadrant 1, that's always the case, and that's important later on. All the other quadrants, that is not the case. So when you look at this one right here, 240 degrees, for 240 degrees, which is roughly over here, angle closest to the x-axis, well, that would have to be this guy right here. Right, and that's the angle closest. That is the reference angle. To figure this out, you're going to have to go 240 degrees minus 180 degrees, because this whole angle right here is 240. This half angle right here, that's 180. So the subtraction will give you 60 degrees, and that is what theta r is equal to, 60 degrees. Okay, that's how you find the reference angles. So these are all housekeeping procedures here for our next couple sections. The last housekeeping procedure we're going to have to do is talk about exact values. And to do that, we're going to talk about the prime trig ratios and special triangles. First of all, recall this. Sine of theta is equal to opposite over hypotenuse. Cos of theta is adjacent over hypotenuse. And tangent of theta is opposite over adjacent. You can remember that using your familiar SOHCAHTOA. This is a saying that is useful to remember. Sine is opposite over hypotenuse, and so on. Okay, SOHCAHTOA. Secondly, what you're going to have is a calculator, and it needs to be in degree mode. Okay, and it should have the trig functions on it. You should be able to calculate both 1 and 2 here. Sine of 50, cos of 22.5. Okay, now there's a couple angles, or 3 angles, that you're going to have to keep in mind. Okay, so all the angles are pretty standard. You type them in your calculator, you get a result like 0.766. Sometimes there are 3 angles, these 3 guys right here, that will yield exact values. Okay, and the reason is because of something called special triangles. So if you look at some special triangles, there are two. Okay, here's one and here's the second one. This is a 45-degree special triangle. That means we have 45, 90, 45 degree with our relationship, or with our side lengths being 1 and our hypotenuse √2. You get this hypotenuse through the Pythagorean theorem. Now, when you look at sine of 45 degrees, sine is opposite over hypotenuse. You remember, opposite over hypotenuse. So, if you look at this angle right here and go sine of 45 degrees, you get 1, right? You're looking at opposite over √2, giving you this value right here, right? So on and so forth. When you deal with 60 or 30, you're going to look at this triangle right here. Okay, you can have these memorized, but you might as well draw the triangle out. You just draw any triangle, put 30 degrees, 60 degrees. Okay, how I remember this is √3 is next to 30. √3 is next to 30, right? 3 and 3. Then the rest has to follow. That's a good way to remember it. Looking at sine of 60, so you go to the 60 degree. Remember, sine is opposite over hypotenuse, so √3 over 2. Now √3 over 2 is 0.866, dot dot dot. So if you actually type this in your calculator, you're going to get 0.866. Your calculator will not give you this result unless it's a fancy one. Okay, but usually they don't. That's why it's important to recognize that it's an exact value. Okay, so now that you know that, let's just calculate some of the exact values. So sine of 60 degrees. Okay, good start. Remember, sine is opposite over hypotenuse, which, when we look at the 60-degree triangle, opposite over hypotenuse, we just did this question. This is √3 over 2. Cos of 45 degrees. Well, cos, right, so cos is adjacent over hypotenuse. Okay. We're dealing with a 45-degree triangle this time. Remember, 45-degree triangle. Okay, you can draw it, but you're looking back, 45 degrees, and cos would be 1. That's adjacent over √2. By the way, you have the answers to all these because I think I listed every single possibility right here. Okay, so this next one, tangent of 60 degrees. I'll try to write neatly. That was pretty good. Tangent of 60 degrees. We're looking at the 60 degree. This is TOA, so that is, I might as well write it out. Opposite over adjacent, the only one that does not use the hypotenuse. Go back 60 degrees. Opposite is √3 over 1, because that's the adjacent. This is √3 over 1. You can write it like that, or simplify it down to √3. And the last one is sine of 30 degrees. Remember, sine is opposite over hypotenuse, 30 degrees, so it's 1 over 2. This is the one example that you actually can use a calculator. If you type in sine of 30 degrees in your calculator, it's going to come out to be 0.5. Okay? But you need to know that 30, 45, and 60, for any of the primary trig ratios, or any trig ratios, will come out to be an exact value. And I expect you to be able to write the exact value, not in some decimal expansion or decimal approximation. So, very important to do these practice problems, because the stuff in this section is basically housekeeping stuff or basic stuff going into the next section. Okay? So, work on that and ask me if you have any questions.